Welcome back to our video module on mechanics of materials. Today, we'll use what we know about how materials act when... Today, we'll pull together our information on how links act in... Today, we'll use what we've learned about how materials act when a force is applied to them to solve a problem that involves multiple components working together. So what should our strategy be in this case? Well, we know that if the force P is applied here, we can fairly quickly find out what's going on in link CD, and we can quickly find what's going on in link AB. From there, we can find out their deformations. The only type of thing we haven't done yet is how do we turn these deformations into information about the deformation at point E. Let's start by writing the free body diagrams for each of these links. So now that we have our free body diagrams, let's identify what these forces are. Well, we can use our sum of moments about point B. Everything's in static, so we're going to set that equal to 0. And we should note that we've put all the links in tension. That way, if we get a negative number, we know it's in compression. Force D times x1 plus P times x2 sums to 0. We solve for force D, and we see that force D equals 23.6 kilonewtons negative. So we know that CD is in compression, and we kind of inferred that already by looking at the problem setup. This would mean force B is only 3.6 kilonewtons. Now that we have the forces, we can fairly quickly and easily identify what the deformations are using this equation right here. And let's put that in purple. If we go through the numbers on that, we see that the deformation in link CD is 0.0003 meters or 0.3 millimeters. Oh, let's not forget that this is negative, indicating it's going to go in the opposite direction of what we were expecting. And the deflection at point B is going to equal 3.6 times 10 to the third newtons times not 0.5 meters, but 0.7 meters, all over 70 times 10 to the 9th pascals, 500 times 10 to the negative 6 meters squared, and that equals 0.00007 meters or 0.07 millimeters. So now that we have the deflection of each shaft, shaft AB and shaft CD, what do we do with that? So the deflection at point E is really a function of geometry. So let's draw a simplified version, simplified line drawing, if you will, of what's going on here. We have A, B, C, D, and E. In white is how things start off. And then AB is going to go into tension. It's going to extend. CD is going to go into compression. It's going to compress. So what we're left, the rigid rod BE, is going to end up looking something like this. Obviously, the question we're looking for is what's going on here. What's delta? Now let's define another point. This point right here, we'll call it F. And this is the point about which the rigid bar rotates. Now if we can define where that point F is, and we'll say that it's X units away from B, we can then figure out what delta is. Well, we have two similar triangles between right here, and right here. So we can set up a ratio between opposite and adjacent equals opposite and adjacent, and that looks like delta B, delta B over X equals delta D over 1100 minus X, and in this case we're going to assume that the units are all going to be in millimeters, and if we use that we find out that X equals 208 millimeters. Great, we're most of the way through. Now we can set up another, let's do this, I don't know, in green. We can set up another similar triangle ratio where this triangle is similar to this triangle. We know delta D over 892 equals delta, the deflection we're looking for, over 1092. Solve for that, and we see that the deflection is 0.37 millimeters. So in summary, we can use our free body diagrams to identify the deflection that certain things experience. From there, we can use our problem setups, maybe geometry, maybe other equations, to help identify the final answer. I hope this gives you a little bit of a better feel of how to attack these more complex problems.